Morning, everyone. Welcome to the second day. So for our first speaker, we have Yohan Brunebarbe, who will tell us about constructing holomorphic functions, universal converse, complex algebraic graph.
Thank you very much, and thank you for the invitation. So yes, in my talk, I will be concerned with complex manifolds that you can obtain with a cover of complex algebraic varieties. So clearly, in dimension one, we know exactly what they are. Not very mysterious. But okay, so P1, C, and the unit disk. But starting in dimension at least 2, this class of complex manifold is pretty mysterious. We don't know much about them. And so maybe let me start to some examples. Well, only a few of them, but in fact, we don't know also many examples. But so okay, so the first kind of example one can think of are just the simply connected algebraic varieties. Because everything is over C, I will not write C again. And so there are plenty of them. So start with Pn, and you take any complete intersection, smooth complete intersection in Pn dimension at least 2. They're gonna be smooth. But they're gonna be simply connected, sorry. More generally, you could take smooth varieties or rationally connected variety. I mean, many class of varieties that that naturally arise in algebraic geometry will be simply connected. It's not that easy to construct a non-simply connected. Of course, I should say that. Not so hard because they are curves. So curve, you think everything. And maybe more interesting examples. We could look at bounded domain in some Cn, bounded symmetric domain. Okay, and so example the unit ball or Siegel-Hall space. And it's a theorem of Borel that each time you take such a bounded symmetric domain, it's possible to find a discrete group acting on it, such that the quotient will be a smooth projective variety. All occur as the universal cover of smooth projective varieties. That's some construction of Borel. In fact, yeah, they come from some arithmetic group in the automorphism group. Okay, so I will just stop here for the examples, but it was to give a motivation for the question that will be interested in my talk. So it's a following question of Shafarevich. So sometimes conjecture, but I think it's a question that you can find in his book, in the third edition of his book on algebraic geometry. So we discussed a bit universal covers of a smooth projective variety. So let's take X smooth projective over C. And looking at the example, you say, okay, basically you have two classes of examples. So you are like the compact one, and on those, every holomorphic function are constant. And you have the second kind of class, so this one where you have many non-constant holomorphic functions. And in fact, using this holomorphic function, you can find a closed embedding in some Cn. So there will be a Stein. And so he's asking, okay, so there is a natural class of complex analytic space that contain the two, the so-called holomorphically convex space. And so he's asking, is it true in general that starting with any smooth projective variety, if you look at the universal cover, so that I will write X tilde, is this universal cover holomorphically convex? I will recall what this means. Okay, so there are several equivalent definitions, but for us, we just take this one. So this means that does there exist a proper holomorphic map so from a universal cover to some Stein analytic space. We call it M. So with M, the Stein analytic space. Okay, so because I'm looking only at universal cover of algebraic varieties, the embedded dimension is bounded. So in fact, the kind of Stein analytic space I will look at, are exactly the analytic spaces that I can realize as a closed analytic subvariety of some CM. Okay. So you can reformulate this question also as follows. Currently, does there exist a map holomorphic proper map to some CM? Okay, so can you distinguish points in the universal cover using holomorphic function up to some compact error proper sum? Okay, so I said the motivation is that by definition, a holomorphically convex space, you see that it's a kind of extension of something Stein by the fiber will be compact analytically. All right. So this is the question I will be interested in. And so it's still open, but there are many results in this direction, and maybe the most important result in this direction is the following result. So it's a theorem of Eyssidieux, Katzarkov, Pantev, and Ramachandran. From 2012. So we start with X complex smooth projective. So I will not state the whole theorem, but maybe what will be important for me. So I fix positive integer n, and so then I can look at the cover of X, so it, which is defined. So I look at okay, so it's MBT of X or from n. Okay, so this is the stack of all local system, complex local system on X of n. Sorry. And so this notation means that I look at the minimal cover of X on which all this local system becomes constants. So in other words, I look at the cover which is defined by the intersection of all the kernel of the monodromy representation of all representation in GLN of C. Okay, so it's some cover of X, and the statement is that in this situation, this cover is holomorphically convex. So in particular, in the case, so if there exists, if your fundamental group is linear, so if there exists a representation from pi1 in GLN of C, which is injective, they prove that in this case the Shafarevich question has a positive answer. Okay, but as you may know, this is not true in general. There are examples of smooth projective variety for which this condition is not fulfilled. So the first example were given by Toledo. But in fact, we give example where the fundamental group is not even residually finite. And it's a result of Malchev that every finitely generated subgroup of some GLN is residually finite. Okay, so this does not settle a Shafarevich question. I mean, basically, so you have this result, and I guess in all the class of examples that we know, their techniques or some variation are sufficient to prove indeed that the Shafarevich question has a positive answer.
One question. So what if X is a projective Shimura variety, then X tilde is a bounded symmetric domain.
Mm-hmm.
Is that a proper holomorphic map to Cn?
There exists one. So not the embedding as a bounded domain, but there is another one.
Okay.
It's not. I mean, already in the case of the unit disk, it's not that clear. There exists a map from the unit disk at some Cn, I guess in C3, but it's. I don't think there is a map that you can really describe explicitly. Okay, so my goal, in fact, will be in the question of Shafarevich, you have some assumptions that are probably too strong. I mean, why should we care only about projective varieties? Quasi-projective varieties are fine too, and they give many more examples of interesting varieties. Also, why should we restrict to a smooth one? And as we see, so the kind of approach here give a result about intermediate cover of X. And so more generally, you can ask if I take an étale cover, infinite étale cover of X, is it holomorphically convex? Okay, so three possible direction of generalization. So what about X singular? I say it's X quasi-projective. And finally, more general covers. But it's false for X quasi-projective. Yeah, you're right. Yeah. So all these three generalizations are false. We'll explain why. What is your example? 2 minus 1 point. P2, yes. So maybe let's start with the first one. First one, I claim that you cannot ask, I mean, this question will be false if you put any kind of singularities. So it's just because if you take a nodal curve, then if you look at the universal cover, it will just be something like this, infinite, it goes in infinitely in both directions, and so it's not holomorphic. So you need to impose some kind of singularity. My thing. The second example, let's do as Pierre safe. So you just take X in P2 minus 1 point and a 0. Okay, so this is simply connected. I remove something codimension 2, P2, it's simply connected. But you easily check using our talks that it's not holomorphically convex.
I wonder about that. If this had a formulation in terms of holomorphic, I was wondering what's convex about this. Does it mean if it lives in something, the functions?
Yeah, that's a good question. So it's another equivalent definition of that. So there is a notion of holomorphic convex rule. So you start with some compact subset of Cn, and you will look at all the subset maybe I explain it.
Do that.
I will, yeah. But so there, yeah, it's really maybe another way to put it is that it's not true that convexity. If you take a convex subset of Cn, it's not a property which is holomorphically invariant. Stable property in convex. I mean, you can have yeah. But now try to find the smallest property which is preserved and contain the convex one. I think that you will get holomorphically convex. But there is another thing that I can explain more about. Okay, so simply connected, but not holomorphic convex. So more generally, if you take any smooth projective variety, you remove something codimension 2, you will have the same situation. Okay, so this is one obstruction.
Ask in one, is there an easy example if you require normal?
No, you'll see.
Okay.
Yes. Yeah, I guess normal is just a good class. And 3 what? Yeah, so the cover. So it's also false because one counterexample would be I take X simple abelian surface. And I will take rho, so it's a representation of its fundamental group. So in this case, it's just it's H1 in Z, which is non-zero. Okay. And what I look at is so the associated cover. I will write it X tilde rho, so the cover that makes this class the class in H1 0. I claim that this cover has no non-constant holomorphic function. There's no non-constant function. So I don't know if there is a proof by hand, but you can relate it a bit to the talk of Jonathan. So it will be a connected complex Lie group, and there is a classification of those that are all product of some C star, some C, and some variety for which you don't have a non-constant holomorphic function. So using this theorem, it's trivial. I don't know if there is maybe a better way to say that. Okay, so but just to say that if you're not careful enough, this won't generalize. But so in fact, if you put some it does generalize to a nice context. And so this is the result I want to say now. Yeah, so this is a giant work with Ben Bakker and Jacob Tsimerman. Okay, so you start with X complex, a normal complex algebraic variety. Everything is complex. Then you take some subset of its Betti space. And so I need to, as I said, I need to add some properties. So the first property is that it is non-extendable. So what do I mean by this? I just mean that you can, so there are all local system on X. I mean that you cannot find a partial compactification of X, which is normal, on which all this local system extend. Okay. So it's motivated by this kind of example. Okay, so here it's simply connected. So, but in fact, the obstruction here is something like the general obstruction would be I have a partial compactification such that the induced map on pi1 is an isomorphism. Okay? So it's a similar condition now, but on all local systems. In sigma. Okay? So in fact, I need to be a bit more careful. The partial compactification could be a Deligne-Mumford stack. Some technicalities, but okay. So this is the first thing which is supposed to handle this counterexample. And we need also a second condition to handle this kind of counterexample. And this condition is what we call absolute Hodge substack. Unfortunately, I will not be able to give the full definition, but I would just want to say that the absolute is a bit reminiscent of the notion of absolute for Hodge class in the abelian case. And Hodge substack is it's a definition we make. Intuitively, it's a subset that has all the kind of compatibilities that come from non-abelian Hodge theory. So any kind of subset that can be defined using some functorial operation will be in this class. So typically, you could look, for example, at the local system with unipotent monodromy at infinity. Would be one example. Or then you can use a pullback, push forward, this kind of. And so in this setting, so we do prove that the corresponding cover X tilde sigma is holomorphically convex.
So some linearity that emerges under this assumption.
Sorry, some
For your group, I mean, one of your enemies, one of the reasons you succeeded is you were a linear group. In this case, is that going to be the?
I mean, so the cover is really defined only using a kernel of linear representation. In fact, you can prove that you can, I mean, any cover like this will be obtained by the kernel of one representation. So it's of the same form. But you make some assumption about its Zariski closure in. Maybe another remark is that, so this is an assumption, but if you start with in the general situation without asking this, you can always make this happen by looking at some partial compactification. Okay, it's not obvious, but there is a way to make things non-extendable by extending them to some maximal extension. What happened in this case? This is because in this case, basically, here in this case, you would look at covers that are defined by Hodge substructure. So in this case, it's not, this theorem is not saying much. If I if I look at this theorem in the case of an abelian variety, what I am saying is that if you look at the covers defined by the sub-Hodge structure of H1, it's holomorphically convex, but then in fact, it's because it comes from a quotient abelian variety. Here, I like to think about this by saying that maybe this should be something in a similar situation. Maybe there is a non-abelian Hodge version conjecture that says that, in fact, this sigma is a pullback from some map to some one, maybe. Or at least those will satisfy all of this kind of condition.
So does absolute in particular mean that it's closed under Galois of C over Q? Or
yes. In fact, part of the definition is that it will be an affine a closed affine subvariety defined over Q. It's part of the definition, but absolute mean more. It means that so you have so because X is algebraic, if you use Riemann-Hilbert correspondence of Berlin, you have a Galois action also on this, and you want that if you apply this Galois action, it stays a Q-bar algebraic subvariety. So it's, I mean, this
by Q-bar algebraic or whatever.
Something. In fact, we show some equivalent with some bi-algebraicity. it's key to prove some result, I would say. I mean, this notion absolutism goes back to Simpson. Right. Okay, so I'd like to start with a proof in in a special case, but which is a meaningful special case. Proposition. So I start with X smooth algebraic, and I'm giving me rho, the representation of the fundamental group of X with value in some GLN, but now of Z, one condition. But I want also that this representation is a monodromy of complex variation of construction, polarized, so CVH. And maybe let's stick to pure, but it would be true also for mixed. For simplicity, let's look at pure. And so the proposition says that if rho is non-extendable, so it's not coming from a strictly bigger partial complexification, then if you look at the corresponding cover, it will be holomorphically convex. So I'm going to give a sketch of proof because it's not that difficult, and it uses, in fact, only classical result that goes back mainly to briefly through. Okay, so proof. So first, I can assume from the beginning that the image of my representation, image of rho, is torsion-free. This is because of the lemma of Zellberg that said that there is always, in this situation, there is always a finite index of group which is torsion-free, and this going to this finite subgroup, it will not change the cover I'm looking at. So it's a small assumption restrict to this case. And so because I have a variation of Hodge structure, I can look at the corresponding period map. So consider the associated period map. So it's a map which is a priori defined on the universal cover of X, but it descends to this cover. So it's a holomorphic map to some period domain for Hodge structure. And because I made the assumption that the monodromy has coefficient in Z, it is discrete, so I can look at the, yeah, we call it gamma. So they are polarized, yeah, it's part of it. It's because everybody was looking 3 letters. But so let's pick it. Polarization. All right, I mean, without polarization, you don't get far.
You have a relation to the integral group, right? So what's the case when it is not a QZPVHS?
I didn't get the question.
Because like you say, it's a model with only a CPVHS, but you have a representation to the integral group.
Yeah, I mean, I could put a Z if you want here from the beginning. It's not
okay. So underlying C, but like it still has.
Yeah. But yeah. Thinking if the polarization is defined over Z or not, right? Not important for what I can say. Okay, so you have the period map and the one downstairs, and it's Cartesian square. Okay, so first, where does this non-extendability condition come from? So in fact, in this setting, there is a result of Griffiths that says that rho is non-expandable if and only if P is proper. And so if and only if the P tilde is proper. Okay, so this will give me some properness properties. Okay, so now I can, because P tilde is proper, I can look at its image by Revert's theorem. And my goal is to prove that S is Stein. And then I will be okay because I will get a proper map to something Stein. Okay, so if you think in the classical situation where you start with a family of abelian varieties, D will be the Ziegler half space. And as I said at the beginning, it is Stein. So in this situation, you are done. Okay? Closed in a Stein. But it's misleading. In fact, most of the time, the period domain have no holomorphic function on them. Okay? In the non-classical case, there are no holomorphic function on period domains. So you need to be.
Okay, Charles, do what? Maybe if let's say this thing's coming from a family of over X.
Yeah.
What does the non-extensible mean?
Yeah. So here I should. Yeah. It's very precise here. So take a compactification, a smooth projective compactification with a normal crossing divisor.
Mm-hmm.
So you have the monodromy around each irreducible component. It's saying that the monodromy is infinite.
Mm-hmm. Okay.
If it's not infinite, okay, it's finite. Okay, if you are in the element forward, you can extend to something. Or if you want going by finite eta cover, but it's exactly, it's equivalent to that. I mean, this is the way Griffiths. Okay, so how do you, under the general situation? So, yeah, so you need to construct some holomorphic function on S. And so for this, you need a tool. And so one very powerful tool to construct holomorphic, to prove that some space is Stein is a theorem due to Grauert in the smooth case and extended in the general case by Narasimhan. That says the following. So if you take a complex analytic space, it is Stein if and only if there exists this space admits so-called strictly PSH, strictly pluri-subharmonic exhaustion function. Okay, so I will not define what it is, but the one important fact about this, why this criterion is very nice, is that so holomorphic functions are very rigid. You cannot do some gluing or patching stuff. On the other hand, the PSH functions, they are very, I don't know what to say in English, but there are some gluing procedure. Okay, so yeah.
Yeah, I'm sorry, like I'm still confused about like non-extendable. So consider like the Torelli map. So it is proper, like the Torelli theorem, but it can still be extended to the NG compact type. So is that violates this definition or something?
I don't see your point.
It's not proper.
It's not proper. Oh, not proper? Okay, maybe.
Yep. So this is one thing, and so then you need to come up with some strictly PSH function, and so then you can apply a theorem of Griffiths and Schmidt, and say that for period domain, so D admits a proper continuous function. So D goes to D to the non-negative real. And so it will be strictly PSH. But so not everywhere, because if it was strictly PSH everywhere, you could D would be Stein. But so only, as usual in Hodge theory, in the horizontal direction. Okay. So if you apply this, you basically get the proof in the special case. I won't give more details, but at least the proof give.
I mean, you just pull it back to any actual analytic thing and.
The thing is that so in this situation, if I am in this situation, if I pull back this function to S, it will give me a proper strictly. I mean, okay, there might be some problem with singularities or whatever, but if I put this under the rug, it gives me a proper strictly PSH function on S. So S will be Stein. Okay. So now if I want to present the proof in general, you see that I will have also two main steps. I said that something which is holomorphically convex, it has a proper holomorphic map to something Stein. So I need first to construct this holomorphic map, and then prove that the image is Stein. So I'd like to explain a bit this, so I guess I will only have time to present the first part. But so unfortunately, it gets much more technical than this special example. But the rough idea is to reduce to this special example. Starting from a general local system, you would like to find some variation of structure, look at the period map, and hopefully construct a similarity. And so this is a theory of the so-called Shafarevich map. I'd like to explain this now. Okay, so maybe I state a theorem and then I explain the link. So same paper. So I start with X normal algebraic. I'm gonna take a representation of its fundamental proof. And for simplicity, I will ask that this representation is non-extendable and also with torsion-free image. Okay, so there are really minor assumptions. I could, to the price of being more technical, I could make them out. But this is the main situation to be handled. And so the claim is that in this situation, I claim that there exists an algebraic, I say unique, sorry. A unique algebraic fibration by fibration, I mean surjective algebraic map with connected fiber from everything normal here. So F goes from X to some in general algebraic space Y, and such that the following is satisfied. So each time I take a connected algebraic subvariety of X, so this subvariety is contracted by F if and only if, when I pull back my representation rho to Z, so I get a representation of the fundamental group of Z, the representation that I get is trivial. So if you never saw such a statement, I think it's quite weird, because so it's a vibration, so it's completely determined by the varieties that are contracted, and I'm saying that the varieties that to contract are those on which a local system, so something topological, gets trivial. So a priori, it's very surprising that already it's analytic, and even more, it's algebraic.
It's kind of like further than this, it's maximally, the same polar, the maximally rationally connected.
So
Those have to certainly go, right?
So there is some kind of connection. In fact, so this kind of map was already so some weak version of this map was introduced by Kolar and company independently. Using so they have the same kind of thing, but they can only handle those subvarieties outside of a countable union of subvarieties, so as in the MLC version. And this is because it's constructed with the same kind of tools like cycle spaces. Okay? So, but if you do cycle spaces, you cannot handle all subvarieties. So then to get this kind of result, we use more a strategy that was first introduced by Eyssidieux in the smooth projective case, using non-abelian Hall theory. And I'm going to explain a bit where it's come from. Yes, but maybe before that, let me make the link with our problem. So there is an equivalent characterization of this map F. So this map F is called the Shafarevich morphism associated to my representation. So I did, always. So equivalently, I mean the equivalence is not totally trivial, but it's not hard. So I claim that rho is a pullback. So it's just an equivalence for the last this property. So equivalently, rho comes from Y. It's a pullback of a representation of the fundamental group of Y. And moreover, if I look at the cover of Y defined by this representation, I claim that it has the following property. So has no positive dimension 1. Compact analytic subspace. So this kind of property, so to have no positive dimensional compact analytic subspace, it's a property satisfied by Stein analytic spaces. But it's not equivalent. But so in my situation, in fact, the map from once I know that this theorem is true, I will get a map from X tilde rho to Y tilde rho Y. So you can check. I said that vibration is proper. So this map will be holomorphic proper. And but the next step would be to show that this one is Stein. Maybe an observation is that here I made no assumption on rho of Hodge type. I mean, I didn't say that there was this Hodge substack assumption. Here there is no such assumption. So so without any assumption, I can still find this weak version of holomorphically convex space. But in general, it won't be true. In general, I need to add this assumption and prove that in the more specific situation, this is going to be found. Right. Okay, maybe a second remark. is to make the link with what I just explained. So in the special case where rho is a modromy of the ZVHS, what is that? So when rho is a monodromy ZVHS, F is a Stein factorization of the associated pair map. So the pair map, it will go from X to a quotient of D by the image of the models. Okay. So it's a consequence of the theorem of the fixed part. It's not obvious, but it's an obvious consequence of that. So in particular, I'm saying that in this situation, if you start with a variation of Hodge structure and you look at the period map, I'm saying that the Stein factorization, so x to y, which is a priori holomorphic, turned out to be algebraic. Okay? And it's something that we proved some years ago with Ben and Jacob. So it's a consequence of the so-called Griffiths conjecture.
Again, the properties, is that that's extendable?
Yeah. Non-extendability gives me property.
Okay.
And so, yeah. So there's some O-minimality coming in the picture, but I won't say.
You have something of absolute odds descends to this y.
Sorry?
You are something of something absolute odds descent from x to y.
Mm-hmm. Yeah.
And you assume variation of odds, mixed odds works also, or admissible mixed odds.
Yeah, it was the same. Yeah. I mean, we need to use it in the general setting. But yeah, we'll explain a bit how they come in the picture. All right, so I'd like to give a really rough strategy of how we prove this theorem. Okay. Okay, so the first thing is that, as I observed, I made no assumption of Hodge type on rho. Yes, but it's in fact the first step of the proof is to reduce to a situation where I can make some certain assumption. Okay, so I'm gonna replace from the beginning rho by the following subset. So sigma is some kind of Shafarevich saturation of rho. So it will be a subset of MBT xn. And it is defined as follows. So I will look at all map from some z to x such that when you pull back your rho, you get the trivial representation of rank n. And then I will take the pre-made by the pullback. Sorry for the I can explain by one.
This image, what kind of group is it? It's a subgroup that's called.
No, it's you mean this?
Rho, the image of rho.
Yes.
It's at GLN.
Mm-hmm.
Can be anything.
Yeah, a priori, yes. I mean, anything.
I mean,
from the
there are
representation.
extra conditions that come from the geometry.
No. A priori. So yeah, that's the first thing is that a priori rho is anything, but I'm gonna replace rho by some subset of the NBT, which now has much more structure. Okay, because so the remark is that if I replace rho by this sigma, Okay, so I'm looking at all the representation that would be trivial on the same variety. So it's something that contains row, but which is much bigger. But now, because it's defined using intersection of some functoriality map, you see that this kind of thing will inherit any kind of structure you have on MBT. So it has a lot of structure. Sigma, and it's an exercise to check that they have the same Shafarevich map, O and sigma. Maybe I will use this one. Okay, so I say rho can be anything. But sigma, on the other hand, is a lot of structure. So let me some kind of so I will not describe. So the structure that we had is this absolute Hodge substack structure. So I will not give you I won't give you the definition, but I will give you some implication. So first implication is that if you look at the local system in rho in sigma, in sigma that have quasi-unipotent modromy at infinity. This quasi-unipotent local modromy. They are dense in sigma. Zariski dense. Okay, so it's so if you take rho to be the whole MBT space, there is an older result of Eno Kerth that proves that the local system with quasi-unipotent modromy are Zariski dense in MBT. And yeah, so their proofs use some Galois theoretic techniques, and we give a proof that use more transcendent functional transcendent technique for this absolute subset. Okay, so it's the first thing, and yeah, you might wonder why do we care? But this is very important for the analytic technique that goes into the proof. This says that the behavior at infinity of some harmonic map that will came in the picture are much nicer than in the general case. So this is the first thing. Well, more importantly, with what I said before, we prove that every irreducible component of MBT, but so of the stack MBT, contains a pure variation of Hodge structure, but a priori only a complex polarized variation of Hodge structure, and you can, with what I said, you can also ask that it has quasi-unipotent modromy. Okay, so it's similar to a result of Simpson in the smooth projective case. So Simpson famously proved that that on MBT there is a C-star action, and that the variation of Hodge structure are the fixed point of this C-star action. And using this, he proved that in every connected component of the coarse moduli space MBT, you can find a pure variation of complex. So, okay, going from connected to reducible is not a big deal, but what is much more subtle and turned out to be really difficult is to go to the stack. The problem being that, so this C-star action already in the projective case, there is a C-star action also on the stack, because if you think this star action is coming from an equivalence of category with the Dolbeault side, with some X bundle, but on the stack, this C-star action is not anymore continuous. So yeah, you have no control of what is happening. And so we need a way to control how the C-star action behave. Okay, so and so for this, we use some twistor theory of Simpson. Watch the Maybe I should explain more what is the subtlety. Is that in general, so the moduli stack lives over the coarse moduli space, and it could really well happen that some irreducible component of the stack get contracted to one point downstairs. And what we are saying is that in this case, this point need to be a pure variation of construction, which is not clear. And then the last property that we prove is that now you have those pure variation of chord structures. So let me take one, V. And so you can look at the deformation theory of this variation of chord structure. And so the universal deformations of V as a structure of so co-admissible C variation of mixed chord structure. Admissible C variation of mixed chord structure. So we don't really care about what it exactly means, but it just means that you have some again some variation of mixed chord structure that control the deformation of my pure variation of chord structure.
Universal, that's something formal.
Yes. Yeah. So we're saying that the formal so this V gives you a point in MBT. So you have the formal the ring, the formal ring of the thing. So it has a mixed chord structure, a full mixed chord structure, but not only that. On it there is the universal deformation, and this one comes with a compatible variation of mixed chord structure. Okay, so what is important to that is that you started with any local system, and out of this, you get a lot of period maps. So this is what you should take out of that. You take a lot of period map, and now you're going to use this period map to construct the Shafarevich map. So, in fact, it's not true. It's only half of the story. Because, as you see, in 2 and 3, I'm getting only complex variation of chord structure. And in what I explained, you need some Z variation of chord structure. So there is also another half that need to be put in the story to get some integrality. So maybe I will finish by stating the corresponding result. This is the following theorem. So it goes back to work of Katzarkov, Suo, Eyssidieux in the compact case. And it was recently extended to the non-compact case in some work of Bordeaux, Daskalopoulos, Deng, and Meze. So what they prove is that if you start with a normal algebraic variety, and pi1, a representation of pi1, but now I want to get some integrality results, so I will look at representation in some QP, or more generally some finite extension of QP. And yeah, so the statement is that in this situation, there exists a map, an algebraic map from X to some S that depend on rho, algebraic map, with the following property. So here there is no unicity in general. The existence will not. So this map will detect integrality. So such that okay, so same kind of assumption. So each time I take the connected algebraic subvariety of X, the map will contract Z. Sorry, maybe not closed. So it will contract Z, and if and only if you pull back your representation, what I call rho Z. So it's a representation from phi1 of Z into GLN of QP. I want this to have as compact image. So equivalently, I want this to preserve a ZP lattice. And so maybe I will conclude by saying, how do you get the Shafarevich map? So by this 1, 2, 3.
That proved by some, that's not a higher rank rigidity. It's proved by harmonic maps, how's that prove?
Where does it come from? Yeah, it's really harmonic map towards the buildings. It's, yeah. Oh, I can explain it later. It's not in 5 minutes. Yeah, so how do you get the map? So from the universal cover of X, you will get all the variation of mixed structure coming from this 2 and 3. And you can add also all map. So I will take all rho in MBT, sorry, not MBT, but in my sigma. In the Q bar point of my sigma, I will take all prime numbers, and I will look at the induced QP bar representation. And I get all kind of map to this S rho P if you want. And the claim is that when you form this, the connected component of the fiber of this map are compact. And so you can form some Stein factorization, and this gives you the Shafarevich map. So here you have some kind of, there is integrality, and there is a Hodge part. And so yeah, over time I will stop here.
Okay, any questions for Yohan?
So can I ask, I mean, sort of implicitly, and of course what you're doing is when you take this sigma, which is the Shafarevich closure of rho, it's like absolutely Hodge in the sense that you said.
Yeah.
How do you prove that? Is that obvious?
So I didn't define absolute Hodge, but yes, it's obvious from, so what was difficult is to come up with a definition that has nice functorial properties. And so one property is that intersection of absolute Hodge is absolute Hodge. One property is that trivial is absolute Hodge. And pullback.
Okay. And also, how far is a general sigma from one of the Shafarevich closures of such a rho?
I mean, in some case, for example, if you start with a very general sigma, the Shafarevich closure will be embedded.
Okay.
But also, yeah. So in fact, each time that you take an absolute Hodge, there will be a very general will be a Shafarevich tense.
Okay.
So the main result, in fact, is about just the absolute Hodge substack, and then there is a trick to reduce.
Thank you.
What is the Toledo example?
What?
Toledo's example, what is it?
Good question. I didn't prepare that. No, but so I can say in a few words. The idea is that so you need to start with a non-residually finite group. So I get the first example given that came up are some central extension of some arithmetic group. So I think so it's some SO, well, it exists for SP2G, and I think there is SO2N maybe. So you have this central extension and you want to realize this central extension as a fundamental group of a variety. So if you are in the quasi-projective case, it will be just like some total space of some C-star over your variety. So it's easy. So the real work is to prove that you can make it projective. And yes, you have to look at the paper.
Other questions?
So it's like, I have a question about maybe sort of general philosophical question, which is like, it seems like it's like a period domain, the Adels or something like that, because you have like over R, you have your period domain, and then you have one for every QP or something. So like if you have like a local system, like a Q-bar local system or something that underlies it, or if the flat vector bundle is defined over Q-bar, is there some period map then to
yeah, so there is not a period map, but there is a harmonic map. So what you should look at is, in fact, there is a picture downstairs. So here you know that the period domain, the fiber over some symmetric spaces, and the composition is just looking at the corresponding harmonic metric induced by the Hodge metric. And so in the p-adic case, so if you start with a Q local system and you fix a prime P, you can look for some nice family of QP non-Archimedean norm. And there is a notion of harmonic such a guy. And so, okay, so the non-Archimedean QP norms, they are classified by some Goldman Iwaori space. It's a special type of Breuatitz building. So it's a singular space, but not so bad because it's like a simplicial complex. So locally Euclidean space.
Yeah.
And yeah, so harmonic map will basically be a map which is when you land in some Euclidean space, it's harmonic.
But there's no higher rank assumption. I mean, in the usual rigidity, like rigidity modulus using harmonic maps, you need to have the fact that you harmonic means you parallel something to get the control of the integrality. You don't have that yet.
No, we're just using the harmonic map. And from the harmonic map, you can extract some holomorphic stuff. And we're using this approach goes back to Gromov-Shane and the people I say.
I mean, they only prove rigidity in higher rank. So this is
it's a different thing. So what you have in mind is this Yao a correlate approach to.
You are proving something that's similar to Selberg's conjecture in that you are showing something, you're controlling the denominator. In the proof of arithmeticity, the key to that modulus control the denominators. Local rigidity gives you something that's controlled without denominators. To control the denominators, you needed to extend this thing to the p-adics, but it seems like you're using just the harmonic map and nothing special about that.
No. We out of the harmonic map, in fact, they are pluriharmonic, so they are really close to some holomorphic object, and then you use this holomorphic object to construct this map. There is no rigidity and by definition, you want to control the fiber of this harmonic map and the other fiber of this.
Okay, if there are other questions, maybe approach Yohan during the break. We're resuming in 6 minutes, so let's take Yohan again.